Merhaba arkadaşlar. Şimdi İngilizceye döneceğim. Şu anki konuşmacımız Justin. Um, Hello, Justin. How are you?
Hello, I'm doing just fine.
Welcome to AWS Community Day Turkey. We are really excited to have you here. So you are from AWS and you are talking about Kubernetes. So this should be very interesting for our audience. And we are looking forward to your talk. And if you don't have any question, I just want to leave you the stage and hear your awesome presentation.
Sounds good.
Okay, so I'm leaving you the stage, and it's all good right now, I guess.
Günaydın, Ben, Justin. That's about as much Turkish that I learned in the 2 weeks of doing Duolingo, preparing for this talk. But thank you for having me, and I'm really excited to talk about some of the things what we're doing with AWS, with Kubernetes, and this project Karpenter. But first, I want to talk about just a little on how I sort of got into Kubernetes and clusters and what I was thinking of when I was building my very first Kubernetes cluster. I was an on-prem environment in a data center, and we had servers, and we bought the servers for it. And I remember my first cluster had 6 servers, and at the time, about as much as I knew about clustering servers was you wanted odd numbers. So I was like, well, I need to have 5 of them, right? So I'm like, well, I'm just gonna use this other one for something else, and I'm gonna use 5 for my cluster. And the other thing that I knew, and of course for like however I wanted to adjust like quorum or something, like I didn't know why, but I knew I needed odd numbers. And I also knew that all the nodes need to be the same, right? Like I wanted all of them to be the same size because any node should be able to take over for any other node. And I needed to have like the same amount of memory, the same processor, and all this stuff. And I really tried to do that over and over again with this cluster. And I was like, this is how clusters work. This is how Kubernetes works. I'm smart, right? Like I should be able to know these things. So I had to really understand why that was always the case, why that was kind of in place. And people thought, hey, a cluster of computers always needs to be the same. And the more and more I used Kubernetes, I started realizing that all of these little jobs we were running, all these workloads, different processes, different containers, they all needed different things. It wasn't that one of them, they all didn't need 1 gig of RAM and half a CPU. Some of them needed 5 CPUs. Some of them needed 10 gigs of RAM. Some of them needed GPUs. And I didn't know what to do with that. Because I always thought that, again, all the nodes have to be the same. But we took this like bucket of what a node meant, what a server meant, and we'd fit all our workloads into it. But all the workloads weren't the same size. And so we either had to create multiple clusters with different size nodes, or we just had to get the biggest node possible that would fit the workloads properly. And that wasn't really ideal because that's just not what I thought we really wanted. And as workloads got bigger and we got more variety of workloads, I figured that I just need bigger and bigger nodes, or I need all of the nodes to have a ton of capabilities, right? Every node needed a GPU and every node needed, the fastest processor. And I started shifting from that into serverless. And I started learning a lot more about like, well, what makes serverless powerful? Why is it that I really care about like serverless being a thing? And a lot of it was just this notion that I could perfectly match the compute needs of my workload and not worry about the rest of it. I didn't need to worry about a cluster or what the other workloads in my serverless, deployments were doing. I could take a Lambda function. I could say I need this much CPU, this much memory, and deploy that. And it was isolated. And it didn't matter. I didn't have to worry about those nodes. I didn't have to worry about where the capabilities came from. And that was a huge change for me to know that like, oh, wow, this serverless thing has a lot of power because I just don't have to think about so many other things. But I still needed Kubernetes for some of this stuff, for some of these long-running processes, for some things that were really large. And I couldn't figure out ways necessarily to get those inside of Lambda or inside of serverless. And a lot of third-party things were just packaged as containers that didn't necessarily run on like a one per evocation sort of situation. So I had to really figure out like how do I get some of the good things that I loved about serverless and Lambda? How do I get those in Kubernetes? And if you've run Kubernetes before, you know that it handles dynamic environments, but some things still like to have these same size nodes. The cluster autoscaler is a really popular project within Kubernetes, and it allows you to scale the amount of nodes you have in your cluster based on workloads that don't schedule. It's workload comes in and says, hey, I don't have enough compute. Cluster autoscaler says, oh, I got you. We'll do this. And it adds another node to the cluster. And you don't have to worry about it, just automatically. But the problem there again is all of those nodes need to be the same. The cluster autoscaler uses heuristics based on how many CPUs it has, how much memory it has, and it adds one to a node group. And it says, oh, this node, we're just going to add one more, and it just horizontally expands it. But it doesn't do automatic things like adding GPUs or figuring out necessarily, I need high availability for this workload, so I actually need to schedule this on a different AZ, a different availability zone, or even different host names necessarily, because the cluster autoscaler is separate from the scheduler inside of Kubernetes. And so all this stuff got really confusing as I wanted to have more and more workloads inside this cluster, because I didn't want to have 5 or 6 different clusters for each different type of workload. I love serverless. I wanted to get back to that simplicity of how do I just get that serverless aspect of my compute needs this much memory, this much CPU, just give it to me. And in Kubernetes, we had to keep adding node groups. And if we wanted them to automatically scale, we have to have the cluster autoscaler know about all those node groups. We had a GPU node group, and we had a small machine node group, and we had a large machine node group, and it depended on which workloads wanted to fit where. And we'd have to match those things with labels and all these things that we had to really control and say, okay, we're kind of putting humans in the way of the scheduling game. And we didn't want that. That's not where humans should be. Humans shouldn't be scheduling those workloads. Humans should say, I just need this highly available. Make sure this just runs in 3 availability zones. I don't really care how you figure it out. Go ahead and do it. And computers are good at that. Computers should be able to figure that side of it out. And that's exactly what we're doing here with Karpenter. Karpenter, I like to call it a workload native scheduler. So you define what you need inside your workload, just like your spec file for serverless or something else, but you tell Kubernetes via some labels and annotations, say, I need these requirements for my workload. I might need a GPU. I need 10 CPUs, whatever it is. And then you go ahead and just send that over to Kubernetes, and Karpenter figures out which node types you want on the fly. Just says, okay, we'll fit you. We'll fit that right in. Whatever workloads are waiting to be scheduled onto a node, we can go ahead and spin up a node for those specific workloads every time. And it gets rid of the notion of node groups. If you've used Kubernetes, you're probably familiar with node groups. And it's just a pool of the same type of machine or the same size machine as many times as you want. Karpenter just says, let's give every workload the exact type of instance type it wants. Sure, we can share those if an instance has multiple GPUs and we want to say, oh, I have 2 workloads that need GPUs, there you go. They can fit on there. The scheduler can figure out a lot of that. But once workloads start going beyond what a node can do or where the boundaries of the nodes are, Karpenter fills in those gaps and says, okay, let's get the exact right instance type for those workloads. And instead of having node groups, we have provisioners inside of Karpenter. We kind of change some of that on, instead of saying someone, infrastructure team says, okay, here's your node group. Here's the GPU one. If you want to use it, use this label. If you want to use this other thing, use this other label. In this case, Karpenter has these provisioners. That's where we tell it like, hey, you're allowed to do this type of instance, or you're allowed to have this many CPUs. There's things like limits. Hey, this group, whoever's using this provisioner, you can only have 100 CPUs. I don't care if that's on 52 CPU boxes or 100 CPU box. It doesn't matter. Your cluster has a limit, and we can set that up inside these provisioners. So we get a little bit more native sort of scheduling constraints based on some of the stuff that Karpenter can do. I can talk about it all day, but I just want to show you. I want to show you some of the things we can do with Karpenter and in Kubernetes that allow us to not even think about it. If I'm a developer, I just want to package my app and tell you what I need. Karpenter can figure out the rest. It'll give me the right nodes. It'll give me the right stuff. And I'm following our getting started guide here. I have a cluster here that I started with Terraform. So I have everything just running in it. I also have a Grafana dashboard here, which we also put in through that getting started guide. You can see how to get this dashboard. Right now I'm looking at pods in my default namespace, and I don't have any. There's nothing running here, so we can see how this works on the fly. And up here, just to show you off what I'm doing here, I have one node in my cluster. This one node is statically defined. I created it while I was creating the cluster. It's a smallish node. It's running the Karpenter controller. There's a couple other, there's Grafana, there's Prometheus, there's a couple other workloads running in this cluster. Doesn't really matter. There's nothing in the default cluster, but they're all running on this one node. I have some deployments already in my cluster that I just put in there. They're examples. It doesn't really matter what it is, but I named them based on some of the things that I wanted to show. So the first thing I'm going to show here is this inflate workload, which is just a simple workload that if I look at it here, we get a container and we say we want one CPU. This workload needs one CPU. This node probably doesn't have one CPU left. It's running quite a few different things. So once I scale this deployment up, or if I was deploying it for the first time, you'll see Karpenter kick in and start adding nodes for me. Or if my keyboard's loud. How many should we do? Let's do 10. I always spelled deploy wrong. I don't know why. Type it right. There we go. Nope. What did I do? I spelled that wrong, man. It's late for me. I'm sorry. It is past midnight. I unfortunately did not get to travel to Turkey this time. There we go. We got 10 replicas. You already see that. Karpenter saw, hey, we have some pods that want to schedule somewhere. They all requesting one CPU. I don't have 10 CPUs available for these workloads. So what did it do? It gave us a C5 A4X large. I'm assuming this instance has more than 10 CPUs. I actually don't know the size off the top of my head, but Karpenter figured it out for me. It was more of a serverless sort of interface where it's just like, hey, my workload wanted this thing. Go ahead and figure it out for me. Karpenter did that. And it's coming up right now. It's been 30, almost 40 seconds. We should see it go fully ready around 60 seconds. This isn't optimized or anything. This is just a default install. Just use Amazon Linux. There it goes. Just under 60 seconds. That's ready. And I can check all of my workloads and they're all running already. So we scheduled 10 workloads. Again, it's not quite as serverless fast, but again, these are for workloads that need a full CPU that are auto scaling or auto deploying in a way that is different than a one per function environment of serverless. So in this case, that's cool. Like I got a node. You can see here that it gave me a on-demand node instead of like a spot instance. If I wanted to have a spot instance, I think I have a very similar thing. I got a deployment here. I just called it inflate spot. Again, we need one CPU and we say we want capacity type spot. So that's the different type of runtime for an instance with AWS. And it's currently 0 replicas. So it'll create the deployment. I can scale it. And again, Karpenter's just going to do the exact same thing. It's just cool. We see now that we had one set there. Now I'm telling I want essentially the exact same thing, but I want a spot instance type. It'll be a little cheaper for me. It's not always guaranteed. It might go away. Some of that stuff is great because I can just save some money in there. And we can see they're all pending here. Oh, actually, you know what? I changed my provisioner and I did not allow Spot anymore. So Karpenter's not going to deploy this one because, again, as an admin of the cluster, I told it no one gets Spots. I forgot I did that earlier today. So that's not going to work, but that's okay. That's not really all the fun stuff. So let's scale that back down. We can also jump back over here and see, oh, you know what? My Prometheus was having trouble earlier today. This better work for me. And I think I lost my connection's still there. Sometimes these metrics take a little bit longer to catch up. We'll come back to it. So you real quick, look at my deployments again. I have this one for a GPU instance type, right? If I ask for that one, you'll see here I have a limit that I'm requesting an NVIDIA GPU. You can guess what's going to happen, right? Like Karpenter's just going to look at that, say, oh, you need a GPU. Here you go. Here's a node in the cluster that gives you a GPU automatically. Don't worry about it. Not a big deal. Again, we can do these requests all the time. As you get to run more things inside of a Kubernetes cluster, there's a lot more requirements that you might have about the types of workloads you're running. You might want them not all to run on the same host for availability, for uptime, for things like scheduling. Because if you notice, my first inflate job, all of them ran, all 10 pods are on this one node. If that node goes away, all of my 10 pods are also gone until they get scheduled again. So in Kubernetes, we call those constraints and tolerations. And we can spread that with different topologies. So let's say I want to have a certain amount spread across different hosts. So I have this job which says, give me these nodes, spread them across hosts. Maximum difference you can have between nodes is 2. So if I scale this one, let's do, I don't know, 30. So if I have a max skew of 2, I'm probably going to get 15 nodes because it probably will schedule 2 per node. And Karpenter is going to figure that out for me. It's just going to say, oh, cool. You want to have as many of these hosts available with these nodes. So I'm going to start scheduling them across. And I have that constraint in here too, where I say, don't schedule it if you don't give me the right node type. If I scroll up here, you can see, I think I probably got 15. Maybe more, because it could also just do 1. If I have that constraint, I can set that up. So these will all become ready, just like, and you can see it actually picked these T3A instance types. Those are X large. This is a medium. That X large is just the right size that Karpenter decided that this workload with these constraints with 1 CPU and 256 megs of RAM, that's what it should have picked. So Karpenter did that math for me. Cool. Humans not in this situation at all. Hostname spread's great. Availability zones spread is probably better because you actually want to, if you're running high availability clusters, high available workloads, you want to make sure that your workloads can sustain a availability zone outage or some disconnect or whatever reason. You want your workloads to still be running. We can double that up. We can use multiple of these constraints inside these clusters, inside the workloads. And the cluster admin doesn't have to do anything. They're not setting anything up. They're not like, oh, well, now that you need high availability, I have to go change something. No. Workloads define the entire thing. So if I look at, I have one that has both. So here's my host name spread, don't schedule. And I also want a zone spread. And I say no more than max use 5. So between my zones, I only want a max of 5 across it. I'm curious if man, this didn't catch up. That's really bumming me out. It has a really cool graphic when you, oh, see, there it goes. Refresh the page. There it goes. So we can see here this first graph. If I make it big for you, here's my spread across AZs. Right. So I have 3 AZs. I have 18 in Central 1A, EU Central 1A, 20 in Central 1B, and 2 in 1C. Like, that's not really what I want, because let's say 1B has a disconnect. 1C is not going to be able to handle that. So I need to be able to do some of this. But again, I don't need to do anything at the cluster level. Workloads can define how available they should be. Oops. We'll double up that spread. Let's get rid of the other one I had. Once they're scaled up, host spread. Scale you back down to 0, because we know we don't just want host name spread anymore. We want host names and zones. We can also get rid of inflate. I just want a clean graph here. And let's make this one 50. Oops. In this case, some nodes already exist. Karpenter may not have to do anything. Scheduler, Kubernetes scheduler, is just going to do the right thing. For all the other pieces that don't fit, all the other nodes that don't fit, Karpenter is going to create nodes in the correct zones. Actually, it already got rid of all of our other nodes. So this cluster went down to 1 node pretty quick. I have it set to a high. You can set Karpenter to like clean up nodes once no jobs are on it. And I have it set to 30 seconds. So once there's a node with no jobs on it, 30 seconds later, it's gone. So Karpenter cleaned up pretty much all of that. And I spelled deploy wrong, which is probably a midnight problem. But I didn't get anything. Now let's try it. There we go. So again, we went back down to 1 node, just running those bare minimum of what we have just to see what's going on. Karpenter itself, Grafana, and just like that, we're getting all of these nodes. And like I said, we have both those constraints here. So we have host name, we shouldn't have more than 2 across different host names, and zones, we shouldn't have more than 5 spread different. So my graph down here, pod distribution by node, will also look different. Before it was actually, we had that host name here, so we could see a bunch of these had 2. This one node had 12, I think, because that was the old deployment. I didn't limit that view to just what it was. Man, I don't know why this is hanging on me. See if I refresh, if I get the correct graph. My data stopped. Let's go back to this. Oh. If I get my zone in here. Oh, that's right. I don't have my labels. My labels are all up here. Anyway, you're gonna trust me, this one worked. Because I don't know why my other graph is. Oh, there it goes. Here comes the data. You can see if I zoom in here, just on this edge, I have 17, 17, and 16 in my AZs. And there's that data. There's the bars I wanted. And you can see all my new nodes that came in, which I'll shift it over here. They're all basically going to have 2 and 1. And so Karpenter, again, figured out that high availability for me. It did the right thing. Other cool things with Karpenter that we're doing is, because your workloads are kind of native in how they get their computes, compute is also native to Kubernetes, where things like, I can list my nodes out. Typically, if I wanted to go, let's say, delete a node, in cluster autoscaler, I can Cluster autoscaler could do that for me. But if I want to do it directly from Kubernetes, I have to go find the EC2 instance. I got to delete it. I got to drain it. I got to do all this stuff to it. Karpenter can handle some of that for us. These nodes have finalizers on them. And so if I do k delete node and tell it just delete that node, I don't want it anymore. Not only does it get deleted from Kubernetes, Karpenter makes sure that the EC2 instance itself is deleted. And if those pods don't fit the same constraints for everything else that I had defined, it'll spin up another node. It'll actually go replace that node, make sure those jobs move. But again, that availability is up to the workload. It's up to how you're defining your workloads to run. And one thing we haven't done yet is set up a pod disruption budget inside of Kubernetes. This is how we define basically how many of those pods we want available to be running at any given time. So if I look at this pod disruption budget deployment, I have at the very top, I set a disruption budget of 80% so that I know I don't ever want less than 80% of my pods running inside this cluster. This is how I want it to run. This is how many I need for my app to be successful. I can shift around 20% if I'm reshuffling, if I have nodes that are going away. All of this stuff can handle it, but I define that again in the workload itself. I don't have to define that inside of my autoscaler or something else. This is just part of your workload. And every workload gets to decide how much availability they want. And so when the node is going down, if it is draining, if I go through and I delete all of these nodes and I have a pod disruption budget, it actually won't let it drain. It won't kick off the nodes until another replacement has been spun up and is running that application successfully. And this just brings all of that power of like how infrastructure moves and how it shifts and what it does right into the workloads. And I love that about Karpenter because again, I feel like it gives me a lot of that serverless power directly in Kubernetes, which has slightly different mechanics of how much power I get, because I can just say, I want this in this AZ. I need EBS volumes from this AZ. I want, different types of storage, all of those things that Kubernetes can do, but I don't have to think about necessarily like everything that I like every last detail of like, oh, this cluster isn't the right cluster, or I need this type of compute. So the last thing I think I'll show off here, just for fun, because I love doing one last demo. Oh, see, I deleted that node, and so I actually scaled down here. Put that back down. One of the other things we're building into Karpenter is just the ability to scale very quickly. We want Karpenter to be super fast for scaling workloads. It doesn't matter if you're scaling 50 or you're scaling 10,000. We want the reaction time and the ability to get a node under a pod as fast as possible. And if you just need to scale fast, sometimes scaling one really large instance will scale way faster than 20 small instances. And so Karpenter can do some of that and say, okay, well, let's figure out how we get that as fast as possible. So if I go, I have this, oops, that's the wrong one. I have a simple script that's just going to deploy a bunch of workloads for me. And all I have to do is give it a number of how many. It bases it off a template. It randomizes how much CPU, how much memory, some of the things that I might want for my workloads. But if I just go ahead and do create workloads, let's make 5,000. Just because 5,000 seems like a good number. It does break them up, but my script breaks them up just into different sizes of deployments to make it a little more realistic. Because again, not all job types, not all workloads are the same size. And so we really want to take that into account when we're scaling this up as fast as possible. So Karpenter can bin pack as many of these workloads onto as few nodes as possible and get them running as quickly as possible. Again, this is 5,000 pods. I actually don't know how long this will take, but we're gonna let it go. You can see my workloads are still being created here. Karpenter is spinning up 24 XL instances. Those are really large. That's going to fit a lot of pods on them, and it's doing that because that's just if we don't have any other constraints set in these deployments, Karpenter is going to try to get those workloads running as fast as possible. It's not even going to worry about, hey, where is this deployment because I didn't set that in my workload. It's just saying, okay, we want these running. Let's get them there. And it actually does a couple tricks on like early binding workloads to nodes so that once the node is available, like that workload's pulling down as fast as possible. So I see a few of them already coming up as ready. My workloads are still creating because I do it in batches of 100. I forgot to set the batch size larger. But let's go back over here. Let's see how this might catch up. They're just starting to come in. So I see the last cycle of metrics, I had 40 containers over here, but that's gonna jump quite a bit here. So creating nodes or workloads. You can see some of these coming in ready. That usually around a minute. We want to get that down a lot lower. We want these workloads, these nodes to be starting way faster than even a minute. For some people, if you're used to serverless and you're used to single function instance, I mean, you're looking at milliseconds. In this case, we're actually creating full VMs, new instances, booting the OS, running the kubelet, pulling down the image. And we're not doing that in a warm pull situation. These are just, we wanted to scale this from zero, partially for an example, partially just to show off how Karpenter can scale this stuff quickly. I see a question in the chat. If I have a lot of AWS credits, yeah, I have the employee discount. So it's for demo purposes. It's free for me because I want to show you what's possible. I want to show how companies are actually using this stuff, and for some companies, like creating a couple hundred nodes isn't that much. This is sometimes pretty small. I'm still creating workloads, man. 5,000 might have been a big number. I just needed to change my batch size. Let's go back over here. Let's see how we're doing. I got 816 in Central 1C. Oh, look, workloads finally finished creating. I know these nodes are all going to go ready. I'm going to have 5,000 pods running in this cluster in probably the next 2 or 3 minutes. But I also know we're at time. And so I'm just going to let it run in the background just because it's fun. But happy to take other questions if you have about Karpenter, about how Kubernetes fits inside of these workload native schedulers, and other questions you might have about direction we're going for it. I only saw a couple people in the chat, so. But that's the end of scheduled presentation that I got. So thank you so much.
Thank you very much, Justin. It was a great talk. So there were a couple of nice comments, like people were telling, definitely going to give it a go. And always a lot of nice tool comments. And maybe like there is this one question, but I guess you answered it, right? But are all types of instances supported? Maybe good to mention again.
EKS, the Kubernetes service, does not support every instance type of Amazon. So the EKS instance types that are supported are absolutely, yes, they are supported inside of with Karpenter. The provisioner is a way that you can set which types of instances you might want. If you don't want someone to use a specific type of instance, you can actually limit that. Or if you only want them to use one instance type. If I provisioner large instance types, I went through the list of instance types, and I I actually weeded out all the small ones. So I had a provisioner that I set up that I said, hey, I don't want any of those small instance types. Don't give me things with like 2 CPUs and under 4 gigs of memory. I don't want those because they're just a lot of tiny ones. And I actually want larger instance types to bin pack more onto each node, depending on my constraints. But you can absolutely set that. Yeah. So I used this and I just went through and created a provisioner that said, I don't want any small instance types, but yeah, anything that's supported by EKS, Karpenter can also look up and use.
Awesome. I mean, we have another question, if you have some time. Does Karpenter work as both scaler and scheduler, meaning it schedules the pods to the nodes it created, or does Kube Scheduler do that?
So for any standard workload that comes into the cluster, Kube Scheduler is going to handle it. Kube Scheduler is still going to be the first place that all those nodes go, or all the workloads go to get placed on a node. Karpenter's just like Cluster Autoscaler, Karpenter's looking for pods that are unschedulable. Pods that say like, hey, I can't get scheduled for whatever reason. Constraints aren't there. Some reason, Kube Scheduler will try to look and say, I can't fit this workload. I'm just going to put it in this unschedulable queue. Karpenter picks it up from there. Once Karpenter has it there, Karpenter will automatically find the correct constraint and node for it, and it will bind it for you. Cluster Autoscaler, the traditional Cluster Autoscaler, will actually find the pod, create as many nodes as it needs, but then it doesn't touch it again. It waits for the scheduler to come back into cycle, and then the scheduler schedules it back. So that actually makes a couple different problems of Cluster Autoscaler has to be the same version of your Kubernetes version, because you have to match your scheduler, how it's working with the scheduler and scheduling or creating nodes. Karpenter doesn't have that constraint because it's actually doing that scheduling on the second pass. And so it skips a cycle of the scheduler doing it. It can do some things a little faster because once it sees a pod that it can control, it does all the rest for it.
Thank you very much. We have one last question. I guess, how does it prefer between M5 and M6i hardware?
It's going to look at every available instance type that'll fit the constraints and the workloads for it. If you have preference, like inside the provisioner, again, you can set some constraints on like what type of run type or how many CPU limits you might want for the entire cluster. Those sorts of things are all part of the provisioner, and the workload has its own constraints. The actual instance type selection essentially comes down to whichever one fits best, and a lot of times whichever one might be cheapest. We have a lot of other things we want to do with Karpenter to allow you to control some of those things too, is saying, oh, you know what, like I want to fit these nodes, but a lot of times there's multiple instance types that'll do the same thing. They'll fit the same job, but one might be a little bit cheaper. And Karpenter in the future, we want it to be able to look at those things to say, hey, on-demand instance, or you ask for spot, which spot price might be cheaper right now? I can give you the cheapest one, and I can fit your workloads and make everything work for you exactly as you would want it to, that it's running, it's available, all the constraints are matched, but we might be able to save you a little bit more money. And so right now, I believe if it gets a list and says 5 of them are available and they all do the exact same thing, it depends how it's doing that, but it's probably gonna pick the first one. It should say, okay, this one looks good. They all fit my constraints. Because again, you'll get multiple matches for the same thing.
Awesome, Justin. I guess that's all. There are no more questions, but we will keep an eye on Slack messages, maybe for a couple of more minutes. So if there are any other questions, thank you very much for your time, Justin. We really appreciate it. It was a great talk.
If anyone listening, feel free to reach out on Twitter too. I'm actually going to go to bed in about 20 minutes, but if you, my DMs are open on Twitter too. So I'll check Slack again probably tomorrow, but Twitter also works.
Yep. Awesome. Sounds great. Thank you.
Thank you.